Hi, my name is Hanzo. I teach and research at Southampton University in the UK, and I'd like to share with you some challenges, solutions, and future research directions in the field of full-duplex wireless communications. This little research adventure is based on a collaboration with Zhang, Keping Long, Athanasios Vasilakos, and myself. Let me commence on a historic note. It's widely known that the plain old telephone actually has only two wires, and yet it allows full duplex communications. And this is due to the fact that a so-called hybrid circuit is used in the plain old telephones, which then assists us in rejecting the transmitted signal from the low-level received signal by simply mimicking the leakage path and creating an anti-phase signal for the sake of cancelling the transmitted signal from the low-level received signal. Now, the same principle applies in the context of wireless communications, but the challenges are significantly more grave. So let me tell you about these challenges in the context of wireless communications. We could use, for example, a Wi-Fi scenario where the transmit power is 20 dBm, the typical receiver sensitivity is minus 90 dBm, and so anything arriving below this level is below the noise level as such, but the received signal level has to be sufficiently above this in order to get adequate detection. So the transmitted signal is 110 decibels above the receiver sensitivity level, and in addition to this, of course, we have also the upper harmonics leaking into the receiver due to the nonlinearity of the associated circuits, and as well as the transmitter noise. So just to exemplify the gravity of the task, the attenuation that we would like to achieve is on the order of 10 to the power 11, and this would correspond to distance which is related to, say, 1 millimeter and 100,000 kilometers. That would allow us to go round the globe twice and arriving within the same spot within an accuracy of about 1 millimeter. So how do we tackle this tremendous challenge? Well, we cannot tackle it in a single step, and in engineering, therefore, we use 3 consecutive cancellation steps as seen at the bottom of the slide. The first step is relying on passive suppression, and I will elaborate on this by simply exemplifying the antenna separation scenario, which essentially implies that the transmit and receive antennas are sufficiently far apart from each other, and therefore there is a path loss between them. Now, this is realistic for a relatively large fixed relay station, but of course it's only to a lesser extent realistic for a portable mobile relay, for example. Of course, what we could do additionally is use, for example, horizontal and vertical polarization in order to mitigate the self-interference. Or another potential solution is to use beamforming, where the transmitter creates a null towards the receive antenna, and that provides us with useful attenuation. Perhaps a minute or two later, I will also allude briefly to the antenna cancellation technique. The second stage of processing is reliant on analog cancellation. And so in this stage, what we try and achieve is create a self-interference inverse signal, and then we deduct the inverse signal from the self-interference itself in the hope that this will cancel the interference. The third stage is, after an analog to digital conversion, the digital cancellation, which can rely on the well-established classic methods of channel equalization, echo cancellation, And so this is also a powerful technique. So if we consider the achievable performance of these different stages, then typically 60 decibels of analog cancellation can be achieved, and 50 dBs or so digital cancellation, but we also have to cater for a peak to average power headroom, if you like. So the challenges are vast in this context. So before I conclude, just a word or two about the antenna cancellation process, just to give you a bit more exposure as to what the paper is all about. So a very useful technique is where we arrange the transmit antennas, a pair of them, at a distance from the receiver antenna so that their transmitted signal arrives in antiphase at the receiver and therefore cancels. So again, obviously, assuming perfect positioning of the antennas, we can achieve perfect cancellation. So looking at the associated signal processing stages, the digital reference signal is created after an encoding and passed on to the digital interference cancellation stage here. But this signal is also digital analog converted, up converted to the radio frequency stage, and then the analog radio frequency signal is entered into a power splitter stage, and this power splitter then creates a reference signal for the radio frequency interference cancellation stage. So the received signal is entered and the reference signal is entered, and then the output signal is entered into the radio frequency analog stage, down converted to the baseband, and then analog digital conversion follows, and finally the signal is entered into the digital interference cancellation. So my hope is that this whistle-stop tool gave you sufficient motivation to look into the paper in some more detail, and my hope is that this will provide you with intellectual stimulation and potentially a few years down the line allow us to double the attainable spectral efficiency of wireless systems.